A single hairline fracture in a load-bearing keystone can bring down an entire concrete bridge. In cloud engineering, a single microscopic syntax error carries the exact same potential for total structural collapse. Programming Language Infrastructure as Code, or PLIAC, allows developers to define their cloud environments using general-purpose languages like TypeScript and Python, rather than static configuration files. Tools like the AWS Cloud Development Kit and Pulumi execute this approach. Writing infrastructure this way transfers the complexity of the system from the individual components themselves to the intricate network of dependencies connecting them. An error in standard application logic usually results in a localized crash or a failed user request. An error in a PLIAC script can instantly expose a private database to the public internet or permanently delete stateful resources containing critical user data. Before any of this code can be deployed, it has to be compiled. The compiler translates the imperative programming language into a directed acyclic graph, or DAG. A DAG is a structural map of interconnected nodes that dictates exactly which cloud resources must be provisioned and in what specific order. Securing this compilation process creates a testing dilemma. Traditional software testing paradigms break down when forced to evaluate these structural cloud maps. This chart plots PLIAC testing techniques by execution speed and feedback frequency. Integration testing is slow and bottlenecks development. Unit testing is fast, but forces developers to manually write massive, complex state simulators. This mock code quickly dwarfs the actual program itself. To achieve high reliability without sacrificing deployment speed, engineering teams are implementing a 3-layered defense pipeline. They utilize structural decoupling, compile-time governance, and automated configuration testing. The first layer of defense is architectural separation. Engineers isolate stateful resources, like persistent databases, into separate deployment stacks from stateless, ephemeral compute resources, like Lambda functions. This clean dependency graph automatically generates a cross-stack reference between a stateless API and a stateful database. But this automated linkage creates a deployment deadlock if the system attempts to delete a base resource still referenced by a dependent stack. CloudFormation runs a strict validation check during deployment. If it detects an orphaned export reference that is still in use by an active stack, it halts the entire process and throws an error to prevent the dependent service from breaking. Engineers resolve this by explicitly defining the dependency order in their code. Using methods like add dependency, they force the deployment engine to strictly sequence the creation and teardown of specific stacks. Alternatively, developers use static helper imports. By importing a resource directly by its known name, like from table name, they pass the necessary reference between stacks without generating a hard, unbreakable link in the CloudFormation template. Structural decoupling and strict dependency management protect stateful data from accidental deletion, but optimizing the architecture does not validate the internal configuration of the resources themselves before they reach the cloud. To enforce security guardrails, the system must intercept the directed acyclic graph after it is structured, but before it synthesizes into a final deployment template. Developers achieve this using AWS CDK aspects. Aspects rely on a computer science mechanism called the visitor pattern. The visitor pattern is a design method where an operation traverses a hierarchical structure, parsing every single element from the top down. First, aspects can automatically mutate the construct tree to force organizational consistency. For example, a single aspect traverses the tree and appends mandatory cost allocation tags to every provisioned resource, ensuring finance teams track exact cloud spending. The second capability is validation. Aspects inspect the tree and intentionally fail the software build if compliance rules are broken. If a developer uses a raw, unencrypted bucket, the aspect identifies the violation, halts synthesis, and blocks deployment. The industry standard for enforcing these guardrails is an open-source tool called CDK-NAG. CDK-NAG applies aspects to run strict pre-built compliance rule packs against the code. It scans for violations of federal NIST or HIPAA standards, catching overly permissive IAM policies or unencrypted databases entirely at compile time. Aspects perfectly govern the static structure of the DAG, but they are entirely blind to the imperative TypeScript logic, the dynamic loops, conditionals, and variables that generate that structure in the first place. Compile-time governance cannot execute or test the internal application logic that dynamically calculates how resources should be configured. To test this imperative logic without writing manual state simulators, researchers developed automated configuration testing, or ACT. This methodology is implemented in frameworks like Proity, a testing tool specifically built for Pulumi TypeScript applications that automatically mocks cloud resources. ACT automatically intercepts resource constructors using runtime mocking, placing an automated barrier between the local program and the cloud definition. The first component, the generator plugin, utilizes fuzzing to bombard the program with randomized data inputs to simulate varying cloud responses. The second component, the Oracle plugin, acts as an automated judge. Oracles use type-based predicates derived from official cloud schemas to filter the resulting output configurations, catching subtle interaction bugs between resources. Because it requires no external network calls, the ACT framework runs hundreds of these fuzzed permutations in a matter of milliseconds. Automated configuration testing enables engineering teams to rigorously test dynamic, edge case logic in their infrastructure scripts, achieving deep mathematical coverage without writing a single line of manual mock code. Infrastructure as code is fundamentally just software, but because of its highly stateful nature and massive potential blast radius, it requires a specialized, multi-layered approach to validation. First, explicit dependency management and decoupled architecture protect persistent data and prevent deployment deadlocks. Second, CDK aspects and compile-time governance tools like CDK NAG enforce strict structural security boundaries before the code ever leaves the developer's machine. Third, automated configuration testing executes rigorous, property-based simulation of the imperative logic, eliminating the crippling overhead of manual mocking. This diagram maps these three layers into a single, unified, continuous integration pipeline. Raw code flows sequentially through the ACT runtime, passes structural validation during synthesis, and arrives clean at the deployment engine. High-velocity cloud engineering requires validating infrastructure mathematically before deployment. Pushing structural and logical testing as far left in the pipeline as possible is the exact mechanism required to scale complex cloud environments safely.